Dichotomy of parallel computing platforms are actually based on two parameters. One is the logical, and the second one is the physical organizations of your parallel platform. So the logical organization is nothing but the we can say that the it refers to a programmer's view of your platform, while the physical organization is nothing but we can refer to the actual hardware organizations of your platform. Okay, there are basically two. One is a logical and the another one is a physical organizations of your platform. Logical organization means refer to the programmer perspective, and the second one is physical is nothing but how we are organizing the different hardware resources at actual, that is nothing but your hardware platforms. Okay, or the we can say that physical organization. So in logical uh, organizations, if you are considering, then there are two components, critical components of your parallel computing. One component is considered as a control structure, and the another one is a considered as a communication model. Again, if you are considering the physical organization, then other two components are considered. One is the shared address memory and the message passing protocol. Okay, so first we will try to cover the logical organization. In logical organization, we are considering two parts: control structure and the communication model. So what do you mean by control structure? Control structure is nothing but how to express the parallel task. How we are going to express our parallel task in control structure. And the communication model is nothing but it is nothing but the mechanism which is considered, which is used for specifying your interaction with the concurrent tasks. Okay, how we are going to interacting with the concurrent tasks. So first one is considered as a control structures of a program. Control structures of a parallel program. In that one, parallelism can be expressed at a various levels of granularity, from instructions level to a processes. Okay, see here, there are two parts of logical. One is control structure and the communication model. Now first we will discuss about the control structures. Okay, so the parallelism can be expressed at a various levels of granularity, from the instructions level to a process. Okay, now what do you mean by granularity? Uh, how we are going to divide your system? Okay, that is nothing but your granularity. There are two approaches for the granularity. One is considered as a cross grain granularity, and the another one is considered as a fine grain granularity. So what do you mean by fine grain granularity? When you are dividing your system into a large number of small parts, then it is called as a fine granularity. And if you are dividing your system into a smaller number of large part. Fine grain is large number of small parts. Keep in your mind, large numbers of small parts, that is your fine grain granularity. And in case of coarse grain granularity is nothing but small number of large part. So basically, if you are considering the granularity in the parallel programming, it divide at a different levels. Different levels is nothing but one is a program level, or another one is your instruction level, like your parallel program also divided at two levels. One is a program level executions, or instruction level executions. So whatever the superscalar architecture, VLIW architecture, these all work on the instructions level. Parallelism algorithms are considered. Okay, now here if you consider the parallel program, so it may be considered as a collections of program, or we can say that it is nothing but the collections of instruction. So whatever the number of instruction, so we are considering the sub instruction, or if the program you are considering, then you are considering the sub task. Okay, whatever the small module you can consider in the program, and that modules are nothing but we are considering as a small parts. So parallelism can be expressed at a various levels. Levels means at a program level or the instruction level. So between these extreme exist a range of models along with the corresponding architecture supports will be there. So if we are considering the parallel control structures of a parallel program, then processing units in the parallel computing either operate under the centralized control of a single control unit or work independently. It means that there are the working of different processing units in the parallel computing. It categorized by two approach. First approach is which using the single control, and in a second approach what we are considering uh, various processing units they are working on the independently. First approach where we're using this, okay, single control unit, okay, and in second approach where all processing units work independently. So according these two, okay, there are two types are considered. One is a SIMD and the another one is considered as a MIMD. Now what do you mean by SIMD and the MIMD architectures? Okay, now see here, first one is a control structure logical organizations of your parallel program platform or the parallel program. uh, okay, so in that one control structure, so there are two architecture in the control structure. One is the SIMD and the another one is MIMD. So SIMD is nothing but if there is a single control unit that dispatch the same instructions to the various processor that work on the different data, then this model is referred as a single instruction stream, multiple data stream. It means that what will be the happen, suppose if you are considering the parallel system, in that parallel system there are number of processors are available. So for all processor what we are going to dispatch, we are going to dispatch only one instruction means suppose if you want to perform the additions of two number, c is equal to a plus b, okay, so same instructions will be sent to each and every processor, okay, but each and every processor having a different their different data, they are working on the different data. So we can say that same instruction is performed by the all processor but they are using the different data, so it is considered as a multiple data stream. Then what do you mean by MIMD? So if each processor has its own control unit, then each processor can execute the different instructions on a different data item. This model is referred as a multiple instruction stream and the multiple data stream. It means here we can see this figure. From that your idea will be clear regarding the SIMD and the MIMD. Now in this architecture if you look at that, okay, there are CPE is nothing but processing elements, okay, so all processing elements are there, okay, or you can consider different processors are there, okay, but there is only one control unit or we can call as a one global unit control unit. And here another architecture is a MIMD where one processing unit element is there and it's having their own control unit. So what happen if you are going to execute here in SIMD addition instruction, then what happen, each processor are going to perform the addition instruction, okay, but in case of that, okay, MIMD architecture there is a processing element plus its control unit, processing elements, another processing elements and another control unit. It means that they are performing the different instructions. Suppose one processing is performing now addition instruction, second processing element will performing the subtraction instruction and like that, okay. So all other processors or the processor different processor they can easily execute the different instruction because what they are having their own control units, okay. So this is a basic difference between your SIMD and the MIMD architecture. Okay. Now for that one, if you are considering, these are the examples of your SIMD processors. Okay. Now here we are considering the one examples how we are going to execute the instruction in the SIMD processor, and what is the difficulty when we are executing the instruction. Is any problem in SIMD processor? Now we'll check it. So here we are executing some conditional statement with the help of SIMD architecture. So first one is nothing but your conditional. If B is exactly 0, then what? You can consider the value of C is equal to A. Else what? If B is not equal to 0, then what you can consider? C is equal to A divided by B. Whatever the, so here what happened? A and B both two numbers we are considering, and the C is nothing but the result. So C is depends on your B. Whether B is equal to 0, then it is equal to A. When B is, if the B is equal to B is not equal to 0, then C is equal to A divided by B. Now for example, here we are considering the four different processors. Okay. Now here you can observe the value of A and B. So here we are considering the different data set. Here A is 5, here 4, here 1, and here is A is equal to 0. Okay. So we are considering the different data set, but we are executing the same. Now first instructions we are going to be execute here. So here if B is equal to 0, then now here you need to check the B value. So processor 0 having a B is equal to 0. So if it is there, then what is the value of C? Then C is equal to A. Now here what is the value of C? A is equal to 5. So uh, after first step or the instructions, the value of processor in processor 0, the value of C is equal to 5 because B is equal to 0. Now consider the second processor number 1, B is not equal to 0. Then what will be the happen? Okay. See here, this processor now in this case, if we are executing the first instruction, and here what happened? The processor 1, in that B is not equal to 0. So this processor will get idle. Then for processor 2, in processor 2 also B value is not equal to 0. Then this processor is also get in idle condition. Now in third, regarding the processor 3, B is equal to 0. So what happens? C is equal to A. Now C का वैल्यू क्या है यहाँ पे 0, तो सॉरी A का वैल्यू क्या है यहाँ पे 0, तो C का भी वैल्यू क्या हो जाएगा 0. Now in first, when we are executing the first instruction, here you can observe that okay, there are two processor which having in that the B value is not equal to 0. That's why these two processor are get idle. Okay. Now consider the second instruction. So if a second part of this code, so B is equal to 0. Now this processor will get in idle condition. Here last processor number 3, again B is equal to 0, that's why it get in idle condition. Now processor 1, B is not equal to 0, so what happen? What is the value of C? C is equal to A divided by B. It means that ये वाला जो स्टेप 1 में कौन सा पार्ट आपका एग्जीक्यूट होगा, दैट इज इफ वाला, एंड सेकेंड स्टेप में आपका कौन सा पार्ट एग्जीक्यूट होगा, एल्स. सो एल्स, that is C is equal to A divided by B. Here again C is equal to A divided by B, that is 1 1, that's why 1 value here. 4 divided by 2, that is a 2 value. So here if you observe that this situation, so in this situation what happened, the when you are executing the your parallel program at the instruction level, so some processor are get idle, some processors are get idle in the different steps. Okay, so this is not actually, in that case we are not utilizing the your resources means there are 4 resources. Okay, so here there is no proper utilizations of the resources in the SIMD architecture. So that is a